What questions do we have? These are going all right? Yeah. Let's do, pardon me, a couple more examples of homomorphisms, and then let's jump ahead to chapter 6 and start talking about ideals, which you've already mentioned a little bit about ideals before. So let's see. Let's look at, this is number 27. So we're actually projecting. So number 27 is on page 82. We've got, let's say, psi goes from R to S, and phi goes from S to T, and both are homomorphisms. And we want to show that if we compose the two, we still get a homomorphism. It is, yeah, it's always flipped, right? So, what's that? Mildly upsetting. Yeah, I get that. You're gonna hate it later. Not today. I'm just later on in the semester. Everything's later on in the semester. That's what I always say, isn't it? You're just expecting one hell of a last week, right? Everything just gets pushed farther and farther and farther along.
It's crazy that we're almost halfway through.
I know it's nuts. It is.
I know so fast.
It's making me want to scream just a little bit.
Just a little bit?
Just a little bit. Like volleyball too, like our volleyball, we're over halfway done. It's like I feel like we literally just like that's crazy.
You only have one more game at home?
Home game, yeah.
That's crazy.
Oh.
That's nuts.
It's actually crazy.
All right, so if we want to show this is a homomorphism, what do we need to show?
And the operation.
Okay, so do we have to show all of those for just homomorphism?
Right? No.
There's the operations, yeah. It does the operations, yeah. So we just need to show that it's operation preserving over both operations. So if you wanted to do isomorphism, you would need to also show that it's one-to-one on two. We can also do that here as well. Actually, that's part B of the problem, is to show that if there are isomorphisms, we also get an isomorphism. All right, pardon me. So, bless you. All right. So, for the operation preserving, we need to show that it breaks up over both sums and products. So, if we start with the composition applied to a sum, so I'll call the two elements that I pick in R just R1 and R2. I could call them X and Y. It doesn't really matter. Just try to emphasize it, or coming from R. So I use little R1 and little R2. What does it mean? What does the composition mean again? When you have phi composed with psi or F composed with G, what does that really mean? Yeah, you do phi of psi of R1 plus R2. Right? And then what are we assuming about psi in this case? What kind of a thing is it? So how can we rewrite the inside? Yeah. And then same thing for phi or phi, whichever way you want to call it. We also assume that it's a homomorphism, so how can we rewrite that?
Phi of sine R1 plus phi of sine R2.
Good. And then both of those then are the definition of composition again, right? That okay? What's the only difference for the proof if you change it to multiplication? Instead of a plus sign, we have multiplication sign, right? So literally it's the exact same proof. You can just write down exactly the same thing you have, just put a dot if you want, or juxtapose it, either or. Everywhere there's a plus sign, right? It's literally going to be the same proof. If both phi and psi satisfy operation preserving, then their composition does as well. Do I need to write it down, or are we okay with that? Okay, all right. So I said that part B also talked about if they're isomorphisms, then the composition is also an isomorphism. In particular, if they're both 1-to-1, the composition will be 1-to-1. If they're both onto, the composition will be onto. And then so it would be an isomorphism. So let's suppose that phi and psi are 1-to-1. What do we start with? If I want to show a function as 1-to-1, what statement do we start with? If I wanted to show that, say, f is 1-to-1, what would your first statement be that we're supposing? Yeah, suppose the outputs are equal, right? And when we get to the inputs are equal. Okay. So let's suppose if we want to show that the composition is 1-to-1, we would suppose that phi composed with psi of R1 equals phi composed with psi of R2. What do we want our final line to be?
Isn't it that R1 equals R2?
Yeah, then R1 equals R2, right? That's what we want to get to. So rewriting our composition as what it really means, we'd have phi of psi of R1 equals phi of psi of R2. But again, remember, we're assuming that both are 1-to-1. Which one do I want to use the 1-to-oneness of first? Do I want to use the 1-to-oneness of phi or the 1-to-oneness of psi first? Get a 50-50 shot if you're just guessing, but which one do you want to use first? The phi, yeah, exactly. Because I have phi of an input equals phi of another input, right? So that's why I want to use the 1-to-oneness of phi. So since phi is 1-to-1, we have psi of R1 equals psi of R2. And then we can say since psi is 1-to-1, bless you. What do we have now if psi is 1-to-1? Yeah, if R1 equals R2, which is where we said we want to end up, right? Hence, phi composed of psi is 1-to-1. Did that have anything to do with them being homomorphisms, by the way? No. This is just a statement about functions, right? And so onto will also just be a statement about functions. So let's say if psi and or phi and psi are onto, if I want to show that just a function is onto, how do I start that? So if I have some function f goes from x to y, I need some new chalk in here. These chalk's tiny. You have some function that goes from x to y, and you want to show that it's onto. What do we start with? What does it mean for a function to be onto again?
Don't we just start with f of something is equal to f of something?
That's 1-to-1.
Onto.
Yeah. Yeah. we just did that one. What does it mean to be onto again?
They map to things?
No, that's still 1-to-1.
I'm right there with you. So I break in. No, let me not.
Let me ask you this: does your set of notebooks map onto the table? Is the entire table covered by your notebooks currently? No.
No.
Because why?
Input smaller than
Well, then in that case, yeah, your input space is smaller, your output space. There's something in your output space that got missed, right? So if your set of notebooks was onto your table, you'd have to cover the entire table, right? So what's playing the role of notebooks and what's playing the role of table? X is the notebooks, Y is the table, all right? So if I want to be onto everything on the table, it has to get hit by some notebook, right? We need more notebooks. So start with an element in here and find something in here that maps to it, right? So anytime you're trying to show something is onto, I want to start with something in the codomain. I want to start with something in the output space. Okay. In this case, if I scroll back up, your composition function starts in R and ends in T. So we want to start with something in T, right? Okay. So your first statement here should be let little t be an element of T, or whatever you want to call it. Start with something in T. We want to find something in R that maps onto T, right? So we want to find, we need an element R in R so that phi of psi of R is T. I need to find a notebook that hits that part of the table. The best visual I had for the time at that particular moment in time. Okay. Now we're not going to find an explicit element that does it, right? It's not something like if you wanted to show that the cubing function is onto, you wouldn't say, I'm going to take the cube root of the thing that I'm looking for, and I'll plug that into the cubing function, and that shows that it's onto, right? I'm not going to find an explicit one. I'm going to use the fact that I already know that I have two onto functions, right? We know we have, it's right up in the corner again. We know we have our phi going from R to S, and we know we have our psi going from S to T, right? And both of those are onto. Which function do you think you want to use first? Given that we're starting with some element in T, do you think we want to use phi first or psi first? Given that we're starting with an element in T.
Psi.
We probably want to use psi, right? Because phi has nothing to do with T, does it? Okay. All right, so we'll use psi first. We're assuming that psi is onto. What does that tell us?
There's an S that maps to that T.
Good. That's exactly right. So,
I have a question.
Mhm.
Did we start? I wrote down in my notes that we started with size artist. Was I wrong?
Oh, did I have it backward?
Oh yeah.
Oh, I do. My bad. Okay, so instead of starting with psi, we should probably start with what? Phi. Sorry about that. You're right. I wrote it backward. Thank you for noticing that. Wait a minute. Oh, that's okay. That's okay. Never mind. All right. Now we've got an element in S. So what function do we think we should work with now? So now I've got an element to S to work with. So what should we work with now? I got back from T to S. Now I can go from S to R by using the psi, which is the correct psi this time, right? So since psi is on to what is true,
There exists R that maps to S.
good. So now if we do phi composed with psi of that R we just found, which is what I'm claiming that's the R we're looking for, even though it's not an explicit element, I just know that it exists. Phi composed with psi is just phi of psi of R. Psi of R is equal to the S, and phi of S is equal to T. Hence the function is on to. Onto is like you have an equation to solve. Right? There's something in the output set, the codomain, the output set. Start there. I find something in the input set that maps to it. So for example, let's do a specific example that has something that we know is onto. So say I had that with my function, I wanted to show that it was onto. So this is going from the reals to the reals, or even the rationals to the rationals, doesn't matter. I would start with, basically I want to solve f of x equals y. I need to find out what I need to plug in to get out y. So it's almost like you're doing what? Finding an inverse, right? So you would add your 2 and divide by 3. So it looks like you do your inverse function, right? Just reversing x and y. But now notice if you plug this in for x, you'll get out the y that you need. Right, so it's like you're solving an equation in that case. This is an explicit example. If I start with y, I need to plug in y plus 2 over 3 to get the y out. Right? Over here, I just know that they exist. I don't have that explicit thing. But another way to think about onto is, can I always solve the equation no matter what I put on the right-hand side? That's another way to think about onto. So notice that, like I said, reals to reals I'm okay. Rationals to rationals I'm okay, but integers to integers I wouldn't be, because this isn't always an integer, so it wouldn't be onto the integers. Does that make sense? Okay. All right, let's do one more, and then we'll start some new stuff. So this is number 37. the first part of 37 doesn't have anything to do with homomorphisms, but it leads into a homomorphism idea. So, do we remember what an idempotent is? I've mentioned it before. Potent refers to power, right? Okay, so what does the idem part refer to?
It's the square. The square is equal to itself.
Good. It's the square is equal to itself. Good. So what this problem says is if E is a non-zero idempotent, that is not a zero divisor, then E is the identity of the ring. So if it's going to be the identity, then I need to show that if I start with an element in the ring and multiply it by that E, I get back to the element I started with, or the other way around as well, right? So as far as the proof goes, if A is an, I'll say the ring is R, then we need to show that AE is E and EA is not AE. AE is A, and so is EA. That's what it needs to be, the identity, right? No matter what element I have in the ring, if I multiply it by the identity, I get that same element back again. All right, so let's start with E squared equals E. Let's start there. That's what it means to be an idempotent, right? How do you think we're going to get, let's start by looking at AE first. How do you think we're going to get A times E involved? What do you think we should do with this equation? Yeah, multiply both sides by A. Pardon me. We are also given that E is not a zero divisor. In order to be able to use that fact, what do you think we should do with this equation? If I want to use the fact that something's not a zero divisor, what do you think we should probably do?
Divide by the E.
Okay, so you're right. That's kind of the idea we're going to use here, but let's think about it in terms of multiplication. So instead of dividing, in order to be able to use that fact, what would I like to see on one side? If I want to use the fact that it's not a zero divisor, what would I like to see on one side of the equation? Don't necessarily know I have an inverse of anything yet. But if it's a zero divisor or a divisor of zero, what do you think I might want to see on one side of the equation? A zero, right? So let's move the AE to the other side. Oops. There's a couple of different things that we can factor out, but remember we're trying to use the fact that E is not a zero divisor. So what do you think we might want to factor out of the left-hand side?
An E.
An E, there we go. So I want to show that E is not a zero divisor, so I probably want a product that involves an E. If I factor, this is actually a technical question now. If I factor out an E, does it go on the left or does it go on the right, the way we have things written on the right? Good, yeah. So this is AE minus AE equals 0. So now I have a product that equals 0. I know that E is not a zero divisor, and it's non-zero, right? It's a non-zero divisor. In particular, it's a non-zero divisor, so it can't be 0. But since the E is not a zero divisor, and I have a product that equals 0, what has to be true?
The AE minus A.
Good. Yeah, the AE minus A has to be 0. And then moving the A back to the other side, we get AE equals A. How would the proof be different to get EA is also A? What would we need to do? We multiply both sides by A on the left originally. Instead of doing that, we would multiply by A on the right. Good. It's literally the same proof, just put the A on the right. But I start with E squared equals E and multiply on the right by A. We do the exact same thing. Move it over. Get 0 on one side. Pull out the E. Now, when we pull out the E, which side does it go on, the left or the right? The left. Good. Again, since E is not a zero divisor, we get that the other piece has to be 0. Remember, we use Z of R for zero divisor. So just use that notation. And then at the very end here, we'll get EA equals A. Our element A here was arbitrary, right? So no matter what element we pick from our ring, A times E is A, E times A is A. So E is the multiplicative identity. Again, if we have a multiplicative identity, there's only one, so it has to be the multiplicative identity. We okay with that? All right. So let's do part B and see how this applies to homomorphisms. Part B says we're going to let phi from S to T be a homomorphism. Now, I need to add a condition to this. There is a homomorphism. No matter what two rings you pick, you can always find at least one homomorphism from ring 1 to ring 2 by mapping absolutely everything to 0. That's always going to work as a homomorphism. It's certainly a well-defined function. It's certainly, you don't have to worry about one-to-one and onto. It's certainly operation preserving because, again, no matter what you plug in, you get 0. And 0 plus 0 is 0, and 0 times 0 is 0. So it definitely is operation preserving. Okay. That's what we refer to as the trivial homomorphism, which is not interesting. Right? So I want this to be a non-trivial homomorphism. So let's do two conditions here. If S has identity, and if phi is non-trivial. Again, trivial homomorphism means everything maps to 0. That's not very interesting. Okay, we usually ignore that one. That one's always 1. Okay, that's always a possibility. But let's assume we don't have that possibility. So if SI is that identity and phi is non-trivial, then phi of the identity in S is the identity of T. We need one more thing. Assume T has no zero divisors. Okay. So how does this relate to the previous part? The previous part said that if we have a non-trivial idempotent that's not a zero divisor, then it has to be the identity of the ring. Right? That was what we just proved. If we have a non-trivial idempotent that's not a zero divisor, trivial, oh, sorry. Yeah, actually, there's actually two technical trivial idempotents. Let's say it again. If we have an idempotent that's not a zero divisor, then it has to be the identity. It's the only choice we have. This one wants us to show that the output is the identity. The output of the identity in S is the identity in T. So what we want to do is show that that output is a non-zero divisor idempotent, right? Because then we can just use the previous part. So we want to show by part A, we want to show that f of 1s squared is equal to f of 1s. We want to show that is an idempotent and that f of 1s is not a zero divisor of T. Oops, not R. If it's an idempotent and it's not a zero divisor, then it has to be the multiplicative identity. That was what we just proved in part A. Let's do the second part first. Let's explain why the identity cannot. Why am I using F? I have a phi and I just changed it to an F. Sorry. Good grief. I'm not good with my letters today, am I? I hate doing that. Well, lots of things I hate, but doing that's one of the things that annoys me more than anything. All right. Let's do the second part first. What's the only zero divisor in T? Zero, right? I should say no non-zero zero divisors in there, by the way, because zero is always a zero divisor. Okay? So we need to show, this part really means to show that we need to explain y is phi of 1s not 0, right? It's the only thing it could possibly be, correct? Let's do this off to the side. If the identity maps to 0, what happens to any other x? How can I write, if I know I have an identity, how can I write x? If we have a multiplicative identity, how can we rewrite x?
X plus the identity.
Well, that would be if it were the additive identity.
Oh.
This is multiplicative. Yeah, there we go. But x times the multiplicative identity, right? Phi is a homomorphism. So how can we rewrite that step?
Phi of X times phi of
Good. But what did we just say that phi of 1 is? 0. And anything times 0 is 0, right? So what does that mean your homomorphism is? Or the entire function is? Everything gets mapped to 0. And what kind of a homomorphism do we say we have? Non-trivial, right? Yeah, so this would make it trivial. We want a non-trivial one. That's exactly right. Okay, so this can't happen, right? So if phi of 1s is equal to 0, then our phi of s, our phi, is the trivial homomorphism, which we don't have. All right. So that tells us that it can't be a zero divisor. Let's show that it's an idempotent. Let's do the other part. Let's show that it's idempotent. So let's start with phi of 1s squared. Well, what does it mean when you take an x squared? What does that literally mean? If I have x squared, that literally means what? X times x. So this would be phi of 1 times phi of 1. But what kind of a function is phi? Yep, so it's homomorphism, so what can we do?
Just do phi squared.
Yep, phi of 1 times 1, good. And 1 times 1 is 1, yeah. What's that? I don't know. You know, there are rings in which 1 times 1 is not 1. Here's one of my PhD thesis. 1 times 1 was 2.
What?
Don't you hate that?
Yes.
Yep. Hence, we have 1 as is a non-trivial idempotent. Oh. Oops. I shouldn't say non-trivial. I should just say it's an idempotent of T that is not a zero divisor. Hence, it must be the identity. Oops, from part A. I keep saying non-trivial idempotent. There are 2 trivial idempotents. What if you have a ring with identity? What 2 elements are always idempotents? 0 and 1, right? So those are the trivial idempotents. Non-trivial idempotents are anything else that are idempotents that aren't 0 or 1. So, for example, in Z6, 3 would be a non-trivial idempotent. 3 squared is 9, mod 6 is 3. So 3 squared is 3 in Z mod 6. So that's an example of a non-trivial idempotent. One of the things that, I'm not going to write this down, so you have to write it in your notes, but one of the things that we care about non-trivial idempotents is that you get an interesting structure in the ring. And we'll see what I mean by this here in a little bit by this notation. But if E is an idempotent in R, then I can break R into pieces. And you're used to breaking things into pieces, right? When you first started learning algebra, well, actually, heck, in grade school, you work with numbers. You break more complicated things into simpler things through factoring, right? If you have an idempotent, and in particular, if you have a non-trivial idempotent, then you can rewrite your ring as a direct product. And I'll talk a little bit more about what this notation means. This means take everything in R, multiply by the idempotent. This means take everything in R and multiply by 1 minus the idempotent. And then you get, and where 1 is the identity of the ring. And you get this structure there where things break up. So you can break it into pieces. When you can do this to a ring and break it into a direct product, we call that the ring is decomposable. You can break it into a direct product. When you can decompose a ring this way, or anytime that a ring is decomposable, you have zero divisors automatically. So, in any event, this is why we care about non-trivial idempotence, because we can break it into pieces like this. All right. In any event, I wanted to play a little bit around with idempotence and talk about the properties of the homomorphisms. Any more questions about homomorphisms at all? It's starting to make a little bit more sense. Okay. All right, so let's jump ahead then. We got about 10 minutes. Let's jump ahead then to chapter 6. Chapter 6 starts talking about ideals. So we've briefly mentioned ideals. What's that?
Hide away from
Is that ideal?
some days.
Some days. All right, so we've talked about subrings. Remember, subrings were closed under subtraction and closed under products of things within the subring, right? An ideal is even better than a subring. It's a subring that's got an extra property that it absorbs all multiplications into the ideal. Okay. So as a definition, if we let R be a ring and I be a subset of R, then I is an ideal of R if first, I is a subring, and 2, even better than a subring, if X is in I and R is in R, then Rx is in I and XR is in I. It absorbs multiplication. The ring may not be commutative, so I need to make sure that I absorb from both sides. That's why I've got Rx and XR. Most things that we'll deal with will be commutative, but there'll be a couple of examples here and there that it's not commutative. If it's commutative, you only need to check one direction, obviously. If it absorbs multiplication from the left, we call that a left ideal. If it absorbs from the right, we call it a right ideal. So both directions is called a two-sided ideal. And if we say the word ideal, we assume it's two-sided. Okay. Just for terminology. Like I said, we're not going to do a lot with non-commutative. There is a couple of examples in the book. That's why I'm mentioning the left ideal and right ideal idea. All right. So, what are some examples of ideals that we've already done? Let's say we let R be Z. Then N times Z is an ideal. If I take all the multiples of n, so for example, we said the evens forms an ideal, multiples of 3 will form an ideal, multiples of 4 will form an ideal, and so on up the line. That's all that NZ means. That's the notation for that. Okay. So we talked about that a little bit before, right? Because if you want it to be an ideal, it has to absorb multiplication. It has to be a subring that absorbs multiplication. Well, subring, we can show that it's closed under subtraction. Well, if I subtract two multiples of n, I get a multiple of n, right? And if I multiply a multiple of n by anything, it's still a multiple of n, right? So if you want to just do a quick little thing, if I do nx minus ny, that's a multiple of n because I can factor out the n, right? You agree with that? And if I take nx and multiply it by any r, that's still a multiple of n. That's what we mean by is closed under subtraction and absorbs multiplication from the ring. But we've already talked about that just with numbers, right? In particular, I think they talk about evens, right? Difference of evens is still even. Anything times an even is an even. It's the same concept. Literally the same concept. So let's do something with a little bit more meat to it. What does that notation mean again?
On the order Z, or not Z, of X.
So this piece right here tells us that that's the thing we're going to use for our variable, and we're going to make polynomials.
Oh, it's polynomials with integer coefficients.
Yeah, so it's polynomials with integer coefficients, right? So this is, I'll just write it in words rather than symbols. Okay, this one is a little bit trippier for notation. Let's see if we can guess what that notation means. Start here. You just told me that was what? Okay. What do you think that does? Yeah, raises everything by 1. So what in particular would the constant term be for all of those? Well, the constant term would be constant term would be. Does a constant term have an x on it? No. Do any of these have any constant term then? No, because you multiplied everything by x, right? You took a polynomial there and multiplied by an x. You said the powers all went up by 1. It's like, okay, so what's the constant term? So the constant term would be here, it would be 0, right? So these would be polynomials with no constant term and integer coefficients. What does this do then? Do you think?
That's an even constant.
Yeah, it has an even constant. So this is the set of all polynomials. Polynomials with integer coefficients and even constant term. Your coefficients it can be even or odd on the x's, but the constant term has to be even, right? Agreed? Okay. So why is this an ideal? Think about why it's an ideal. Okay. If I take two polynomials that look like this and subtract them, I'm going to just talk it, and then we'll come back to this example on Thursday. But think about why it has to be an ideal. If I subtract two polynomials and their constant term is even, what's the constant term of the result? Even, right? Because you just subtract the like terms. So when you subtract the constants as an even minus an even, which is still even, right? If I take something with a non-zero or a constant term and multiply by an even constant term. It's just how do you get the constant term of a product of two polynomials? You just multiply their constants, right? Because if it has an x in it, it'll still have an x in it when we multiply. So if I do a constant, any constant times an even constant, I get an even constant. Right? So it'll absorb multiplication. Like I said, we'll write out the details next time because I want to make sure I get time to get over there. But anyway.